We know that the first law of thermodynamics governs changes in the state function, we called internal energy. The changes in the internal energy are closely related to the changes in the enthalpy, which is measure of the heat flow between a system and its surroundings at constant pressure. We also learned previously that the enthalpy change for a chemical reaction can be calculated using tabulated values of enthalpies of formation. This information, however, does not tell us whether a particular process or reaction will occur spontaneously.
For many years, chemists and physicists tried to identify a single measurable quantity that would enable them to predict whether a particular process or reaction would occur spontaneously. Initially, many of them focused on enthalpy changes and hypothesized that an exothermic process would always be spontaneous. Although it is true that many, if not most, spontaneous processes are exothermic, there are also spontaneous processes that are not exothermic.
The direction of a spontaneous process is not governed by the internal energy change nor enthalpy change, and thus the first law of thermodynamics cannot predict the direction of a natural process. The second law of thermodynamics comes into play in determining spontaneous reactions through the introduction of the concept of entropy. Entropy is a thermodynamic property of all substances that is proportional to their degree of disorder. The greater the number of possible microstates per system, the greater the disorder and the higher the entropy. In simple terms, the higher the entropy, the greater the disorder in a system.
The second law of thermodynamics states that in an isolated system, the entropy will always increase over time spontaneously. It suggests that for a spontaneous process to occur, the entropy of the system should be increasing naturally without an external force pushing to it to do so. The example of the fusion of gas from low pressure to high pressure is not spontaneous because on the surface, the process of diffusion is a mass transfer possible through a difference in concentration of particles and that it operates such that the particles from the more concentrated area transfer to a less concentrated one.
In gaseous system, concentration is directly proportional to concentration and to be generally used interchangeably with correlation. That is to say, that a high concentration system is also a high pressure system, and that diffusion operates transfer the gas from high pressure to low pressure. The concept of concentration and pressure can visually explain and relate entropy increases this system. The system below depicts a low and a high pressure system in terms of their concentration for visual representation.
Figure 1 shows a low-pressure system where the particles have more than enough space to move around. When the system in Figure 1 is pressurized by decreasing the volume of the container, the particles have less room to move around and are in close contact to one another, making them more packed and thus looks more organized. Upon inspection, the system in Figure 1 will have more freedom in the movement of its particles. It is therefore in a greater state of disorder than the system in Figure 2, and based on the second law of thermodynamics will be a more favored state because of high disorder mean high entropy. This means that if the system in Figure 2 is allowed to reclaim its initial container size, it will spontaneously want to achieve a state of greater disorder like that of the system in Figure 1. Figure 3 below shows this spontaneous process.
As one continuous system, the pressure gradient of gas can be linked to opening a bottle of soft drinks. Upon opening, the cap pops. This is because the carbon dioxide gas inside the bottle is released into the atmosphere. which is of the lower temperature than the inside the bottle. Under natural conditions, the other way does not occur. Without an external force, the diffusion of gas should go from a high pressure area to a low pressure area.